So now we will see the quick revision of the read operation in the SRAM cell. So here we have on one SRAM cell, and let us assume the data is Q is 1 and Q bar is 0. This is basically data that is stored inside this cross coupled inverter, and we have some access transistor M5 and M6. Okay, and we have here bit line bar and bit line. These are the data line. So we have some capacitances associated with this bit line bar and bit line, that is basically CBL bar and CBL, and this capacitances comes from the some parasitic capacitances in the line as well as the capacitances of the MOSFETs. Okay, so what we do initially, we basically charge up this capacitor CBL bar and CBL to VDD. So the initial voltage over here as well as over here is VDD. Now what we do, we basically assert the high voltage, that is the VDD, to word line. That means we activate the word line, and that basically activates the M5 as well as M6. Now if you see carefully that the CBL bar has a path to discharge, that is this particular path. Let's see why. Because see, the Q bar is basically 0, so potential over here is 0, and this is VDD. So as the M5 is on, so it can discharge through this path, and then you can see M1 is on, because M1 is the N channel MOSFET, and the gate of this N channel MOSFET is connected to directly Q, and Q, that is equals to 1, that is equals to VDD. Okay, so M1 is on and M5 is on, so it is discharging through this path, M5 and M1. Okay, and now if you see the CBL, okay, so potential over here is VDD and potential over here is also VDD, because Q is 1, so it cannot discharge through this path. So the potential over here will be, it will stay at VDD, but potential over here, the voltage over here, it will discharge very quickly through this path, depending upon the resistance on the path. Now what we want, the crucial thing is that once it discharges through this path, the voltage drop across this M1 increases. So but we want that this particular voltage should not be greater than the threshold voltage of inverter 2, because this particular point is directly connected to the input of inverter 2. If the voltage over here is greater than the threshold voltage of inverter 2, then what will happen, it will flip the state of this inverter. Okay, the state of this inverter. So that's why we choose the on resistance of M1 to be very less than the on resistance of M5. Then the voltage drop over here is very small. So how can we obtain this on resistance of M1 to be very small? We know the on resistance R is proportional to 1 by W by L. Okay, so we choose the W by L of transistor 1 very greater than the W by L of transistor 2, transistor 5. That is basically our cell ratio. Okay, so this is how we can define the cell ratio, and we can ensure that our transistor, whatever data was there, is retained in the data while the reading operation. And how we are reading, we are basically once it discharges through this capacitor, discharges through this path, the data on this line is 0, that is basically your BL bar, and the data over here is BL, because this capacitor cannot discharge. So you can get the data from this BL bar as well as from this BL bar as well as from BL. So this is how we can read the data from the SRAM cell.